So good afternoon, everyone, and welcome to the School of Public Health's noon meeting, which is hosted by the Division of Occupational Medicine. And I'm Dr. Itumeleng Datamala. I'm a senior lecturer in the division, and joining me is the head of the division, Professor Mohammed Jibai, who has kindly allowed me to chair this session. So we're quite fortunate today to have CK, Dr. Kamanzi, joining us, and she'll be speaking on some of the work that she's been doing, which focuses on the impact of coal mine dust, and particularly looking at the pneumoconiotic potency of the various coals. So very briefly, Dr. Kamanzi has got a very illustrious CV. So she has a PhD in chemical engineering from the University of Cape Town and is currently a postdoc fellow under the mentorship of Professor Mozam Jacobs. So through her PhD research, Dr. Kamanzi has investigated the complex relationships between the physical, chemical, and mineralogical characteristics of coal dust. And of course, very pertinent for us today is looking at the toxic effects of these, which is looked at in lung cells in vitro. So she will be presenting aspects of her recent review paper, which was titled The Impact of Coal Mine Dust Characteristics on Pathways to Respiratory Harm, investigating the pneumoconiotic potency of coals. So a very warm welcome to you, CK, and welcome, of course, to Megan and your other collaborators on this paper. Over to you.
Thank you very much, Itumeleng, for that introduction, and thank you everyone for your time today coming to listen to the talk. As I was introduced, my topic today, I'll be speaking about aspects of my recent review paper, which is entitled The Impact of Coal Mine Dust Characteristics on Pathways to Respiratory Harm, where it specifically investigated the pneumoconiotic potency of coals and what that means. So in terms of the big picture problem, mine dust is a critical issue for the respiratory health, not only of mine workers, but also proximal mining communities. Historically, mine dust has been linked to epidemic levels of disease burden, with the most notable diseases being silicosis, asbestosis, and coal workers' pneumoconiosis, which we'll refer to as CWP. As part of a global burden of disease study, it's estimated that approximately 1.3 million deaths resulted from chronic respiratory diseases such as pneumoconiosis, contextualized in 2019. In a separate study, CWP was found to account for approximately 25% of all pneumoconiosis cases in 2017, just to contextualize the breadth of this issue. So in the review paper, in the review paper, I looked at the historical advancements in the management and mitigation of coal mine dust diseases, and I looked at this across a 200-year span of the problem. The full timelines are included in the paper, but I've taken key aspects out for us to discuss today, so some of the time points are going to be missing. So to start off, let me get the laser pointer. As the starting point, pneumoconiosis as we currently know it, its first pathological description was described in 1831. And up to the point of 1918 in Britain was the first legislation passed to compensate workers who had developed health effects from silica dust exposure. And at the time, coal dust related diseases were sort of combined with what was already well established as silica related health diseases. So later on, sort of around in the 1930s, were coal dust related diseases actually separated and classified as their own needing their own pathological description, and therefore separate set of management strategies related to those specific diseases. In that time of the 1930s was a resurgence in coal dust related diseases within British collieries. And at that time, the Medical Research Council in Britain started the first epidemiological survey.
I think you decision is then was it you asking or saying or
I'm
speaking to me
sorry.
once about
Sorry about that, CK. Could I ask everybody to mute themselves, please? Apologies, you may continue.
Thank you. So the first epidemiological survey conducted by the MRC in Britain was conducted during the periods from 1936 to around 1942. And as the report suggested from that survey, simple pneumoconiosis was proposed to be prevented if the dust concentrations were reduced, and they suggested a management strategy to monitor this would be to measure the mass concentration of dust in the air. So that was the first onset of what could be deemed the first management strategy for tackling coal dust related diseases. In the 1950s, a pneumoconiosis field research program was established, and they had conducted their own set of epidemiological surveys, which spanned from 1952 to 1967. And at this time, the US had also started bringing in legislature to protect the respiratory health of coal mine workers, where they implemented the Federal Coal Mine and Health and Safety Act, and started the National Study for Coal Workers Pneumoconiosis, which enlisted a first cycle of epidemiological survey. And from these different surveys that occurred, there were dust limits set out both for British collieries as well as for American collieries. So during the time period of the 1970s to the 1980s, a lot of fundamental research was being done to explore on an experimental level what are the toxic agents responsible for the pathogenesis of coal, and what hypotheses could be postulated for the pathogenic pathways from coal exposure in the pulmonary environment. And one of the hypotheses that was generated was that various cycles of damage induced from these reactive oxygen species derived from the cells, particle cell exposures, produced a continuum of inflammation, which then progressed to disease development. And this fundamental research looked at sort of the first descriptors of what components in the coal can be used to describe what we can say is the pneumoconiotic potency of that material. And that was what could be described as the beginning stages of a secondary strategy investigating what aspects of the coal are most toxic that we need to manage. So because of the large-scale epidemiological studies that were occurring during this time, there was less of impetus to carry on with the fundamental research on the toxic agents, because the data that was coming through was showing that the reduction in dust exposure was effective in reducing the prevalence of CWP. And this was mostly expressed by American studies, the American case. But closer towards the end of the 1990s, the beginning of the 2000s, there was a resurgence in the cases of CWP in the US. And this resurgence was non-uniform between the different regions, in the sense that certain regions had higher prevalence rates of CWP and its more progressive endpoint, progressive massive fibrosis. So a more severe case of CWP in certain regions than others. And that's where the research began to look into the toxic, academic research began to look into the toxic agents, and this notion that bioavailable iron in coal sourced from certain minerals within the coal could lead to reactions that influence the balance of these reactive oxygen species and then progress disease development in that through those mechanisms. So in the early 2000s, there was a study, the first study of its kind, which incorporated the particle characterization data with epidemiological prevalence data across the US. And that study looked at how the mineralogical and how the mineralogical changes in the coal between the regions could map to the differences reported in the prevalence of CWP. So in parallel with this kind of research, the practical implementation of using dust monitors in the workplace and reducing the limits on dust exposure was still being implemented well into the 2010s. However, when we get to the 2017, 2018, 2019, we see the overwhelming evidence of the extent of the resurgence in the US, and studies began to investigate in more depth, generating these data sets on how the dust particle characteristics differ between operations within the mine and also between mines of different regions. In 2019, in particular, there was an epidemiological investigation into the nature of CWP prevalence in the US, where they saw a distinct increase in silica-related pathology. And they linked this to the implementation of thin seam mining, which incorporated less of the coal material and more of the wall rock, which had quartz-rich minerals. So that increased the amount of quartz dust in the air. That was the proposition for this increase in silica-related CWP. So in the 2020s to 2021, there was a huge effort in terms of developing data sets that could be used to link, developing particle characterization data sets for the purposes of linking them to toxicity related data to flesh out this idea of what makes certain coals more toxic. Sorry. Okay, they're muted. So this is, again, fleshing out that idea of what is the pneumoconiotic potency of a coal and sort of driving into this second management strategy, not necessarily looking at exposure, but looking at what are the factors that make coals inherently toxic. And in 2022, following the discovery of the silicosis type, the prevalence of silicosis type CWP, a follow-up study found that pathological data as well as mineralogical data supported or demonstrated that crystalline silica was the major cause of severe pneumoconiosis observed in the CWP resurgence. So they found that the silicosis type CWP was actually the most prominent type of that characterized the resurgence. So in the case of the American context, the change in mining mode was the driver for the anomalous resurgence, the anomalous regional differences in CWP prevalence. In terms of additional research from the Australian branches, there's been a focus on using different statistical techniques to really understand the relationships between the characteristics and the toxic responses. So what do we do with that those two types of data sets, and how do we effectively move towards defining pneumoconiotic potency, as well as describing the various mechanisms past that point. So now that you have a baseline understanding of the management and mitigative strategies, I want to talk about coal as a geoanthropogenic dust source. And what I mean by geoanthropogenic is that coal is a geological material which composes of organic material, which is the carbonaceous matter, as well as inorganic material, generally speaking, which is the mineral matter. And this has inherent properties based on how it was formed in its geological context. But anthropogenic activities such as the mining, cutting, excavation, processing of the material can change those inherent properties. So we transform the primary material into dust, and depending on the mechanism by which it was transformed, whether it was cutting or crushing, you can have different distributions in the particle size or the shape of the particles, as well as processing might change the composition of the materials themselves. So we now alter the material and create different source populations of dust. So in terms of the coal mining context, you have two mining modes, which is the underground mining and the open cast mining. So in terms of how literature has characterized the different dust populations that occur in underground mining, it's generally been seen that mineral composition varies significantly between mine locations, so between mines and between operations. So how the mode of generation of the dust. Cutting sites have been found to yield high proportions of mineral matter, which again links back to the cutting of the wall rock in thin seam mining as opposed to the ore material. So you get more of an inclusion of different types of minerals as opposed to just the primary coal. And then you can have particle sizes were found to vary between activities. So you have cutting zones which yield higher proportions of fine particles, which is as to be expected, as well as you have the inclusion of diesel particles from the machinery, which also contribute to that particle size distribution. In the open mine cast setting, ore excavation, transportation, and handling of the ore have been seen as the activities which produce the most dust. Each activity was found to produce distinctively different distributions of particles, particle sizes, and chemical compositions. And dust produced from tailings or dump sites, tailings handling, so the dumping of the waste material to these dump sites, as well as the truck traffic, where the trucks are picking up dust as they are moving, as well as between transporting loads, there's potential for dust emission. More mineral, those two operations have more mineral matter compared to the coal face. You have a higher abundance of fine particulates from tailings handling, so dump handling, and truck traffic compared to the work face. And this has been rationalized by the fact that there is dust suppression, there's wetting happening at the coal face, which agglomerates the particles in suspension. So you tend to have coarser particles than just at the transportation sites and the tailings handling, because there isn't necessarily dust suppression at the same level, same frequency. All right. So moving into, I suppose, more familiar side. So in terms of the fate of inhaled particles, this is a diagram which you very often see when you're talking about dust. Where do the particles end up in the anatomy of the respiratory tract? And I'd like to highlight a few points here in terms of this can depend, the distributions in terms of what sizes get deposited where depends on how you are breathing. So I have two figures here which look at normal nasal breathing versus oral breathing post light exercise. And here in normal nasal breathing, we see that there's not a lot of deposition happening in the lower respiratory tract between the trachea and the bronchi and the bronchioles. And really up till 1 micron, you see a lot of the particles being deposited in the upper respiratory tract, the nose and the pharynx. And then past 1 microns, you have a higher probability of particles being deposited in the alveolar region, which is really where you start to see immune responses. And in terms of oral breathing post light exercise, you have a lot more particles being deposited in the lower respiratory tract, as you would expect, not a lot being deposited in the nose. But what's interesting is that you have a slightly coarser range of particles being deposited in the alveolar region. So it's something to note, because that is something to contrast when you're talking about an occupational setting. People will be exerting themselves. So here I want to talk about give a generalized description of the disease induction pathway, which is sort of correlated from what is understood to happen between the particle cell interactions and disease development. So when I talk about this disease induction pathway, I'm speaking about this in the context of particles which have entered the alveolar region and are interacting with phagocytic cells, the alveolar macrophages. So the dominant pathway is staged through a production of reactive oxygen species post particle cell interaction, and this is part of the defense mechanism of the phagocytic cells, and is an expected response. But the particles themselves are also known to potentially chemically react and produce ROS of their own through their own mechanisms. So in the event that the antioxidant defense systems, which are meant to counteract the production of these radicals, are effective, then the cells are able to manage the influx of foreign particles. But in the event that they are ineffective, then you end up with a state of oxidative stress, which is an intense period of attack represented by an overproduction of these reactive oxygen species, which then leads to can lead to further degradation of lipids, your cell membranes, and potentially damaging the DNA. So as this progresses, there are this elicits an immune response within the pulmonary environment, and this acts as a feedback mechanism which brings additional cells, as well as perpetuates immune signals that prolong the state of cellular stress and inflammation, and eventually result in cell death and tissue damage. And when this occurs on a chronic level, this eventually develops into the types of diseases that we see, such as CWP. And this is the predominant pathway that is ascribed to coal dust related diseases, but there are additional pathways which I'm not going to go into, which are ROS independent, leading to direct cytotoxicity, as well as genotoxic pathways. So now something different. I wanted to talk about some of the factors that influence particle toxicity from a particle perspective. So this is going to sort of be coming back to that idea of, geoanthropogenic sources. So how the various generation modes or the inherent properties of the material may be altered to create these new sources, and what that means for the toxicity of the particle. So if we start on the left-hand side and we look at specific surface area and particle size, if you have particles with greater specific surface area, then you have greater surface area for reaction. So operations which produce much finer dusts can be quite detrimental from a reactivity perspective. So the next particle parameter that I want to talk of is encapsulation versus liberation, this idea of mineral texture. How are minerals associated with one another? Because this has an influence on the reactivity of the mineral. So it's not only about the presence of reactive minerals, but whether they have available area or whether they are covered by minerals which may serve as protective agents, or whether active agents are being locked in non-reactive phases and therefore enabled to release active components that could contribute to some of these mechanisms that I highlighted earlier. So the next parameter is crystallinity and weathering. Crystallinity in terms of the surface structure and the availability of surface defects plays a role on the chemical reactivity of the mineral surface, as well as its ability in terms of some kinds of minerals such as quartz to produce these reactive oxygen species. In terms of alteration, if minerals come into contact with water and oxygen, which you'd readily find in a biological context, they can actually alter to non-reactive forms. So you may have a reactive form of an iron sulfide, such as pyrite, and in the event that it is altered to what we call an iron oxyhydroxide, which is not it's not able to release iron in the same way that a sulfide mineral is able to. So the state of weathering plays a role on how reactive the mineral is, and this can even be a function of how weathered the material has been prior to inhalation. So for example, if material has been sitting in tailings in a dump, it would has a chance to interact with the elements and could potentially weather into non-reactive forms, or more easily bioavailable forms such as salts, which can release metals. The last parameter that I want to talk of here is mineral associations and element distributions. So certain mineral associations can counteract the effects of others. And here I give this example of pyrite, which is an iron sulfide, and a calcite grain. And pyrite in certain systems can release acidity, but this acidity can be mitigated by the buffering capacity of carbonate phases. So that can change the pH of the system. But if you have a acid generating material, the pyrite, with an inert mineral companion, then that can leave your system fairly acidic. So the associations can also have implications on the pH of the system. And in terms of the element distributions, you can have certain kinds of key elements such as iron, which is known to react through mechanisms leading to the generation of reactive oxygen species. And you can have iron present in different forms, different mineral forms that would either make it more easily bioavailable through dissolution or not. So where your element is distributed, in what mineral phase can sometimes be the difference as to whether it is released into the biological environment or not. So the last aspect that I want to talk about is the utilization of coal particle characteristics to assess the potential respiratory harm. So how do we actually start to define pneumoconiotic potency? So to preface this, the complex reactivity from particle cell interactions is well documented for coal mine dust, and particularly for composition-driven reactions in the lung. But despite this, there is still uncertainty on the relative impact of composition and particle morphology on oxidative stress and inflammation. So basically what I'm trying to say here is that it's challenging to try and understand the relative impact of different classes of characterization information to get a holistic understanding of what is the impact of, say, for instance, particle shape as opposed to particle composition. So in terms of the approaches in the literature, there are studies that have constructed multilinear models to assess the relationships between oxidative potential and composition-based data. And the advantages of this way of trying to define pneumoconiotic potency is that you're able to model the relationships between a combination of parameters. But the issue here is that often a lot of these composition-based parameters are actually related to one another. So you have this confounding factor of collinearity. So in a second approach, studies have looked at aggregating multiple parameters of toxicity using principal components analysis, and then correlating this aggregate value with a range of particle parameters. So now you're not limited to just composition-based data, but you can look at other physical parameters. So an advantage of this is that you get to actually assess the collinearity, because now you're looking at associations rather than modeling relationships. And you can also look at the combined effect of multiple responses to those parameters. The disadvantage of this approach is that it doesn't provide information on the relative significance of correlated parameters. So I don't want to reveal too much about the paper that we're just going to submit, but we have some interesting work coming up that would kind of build a bridge between these two approaches. So just to end off the presentation, some take-home points is that, or some take-home points that I think are critical from the paper, is that understanding the burden of coal dust diseases is a critical issue for countries whose CW prevalence baseline is greatly underestimated. From the timeline, you could definitely see that there was a lot of information coming from the global north, a lot of studies, a lot of epidemiological data, but there really isn't that much coming from countries within the global south. And there is definitely a need to adequately contextualize what disease burden is in that context. Understanding how particle characteristics can potentially vary based on geological and geoanthropogenic factors provides a valuable information for dictating different types of mine dust sources. And this in itself could have implications on how to develop more targeted management strategies per source identified on the mine, because different sources may lead to different endpoints. Lastly, the physicochemical and mineralogical characteristics of coal mine dust play a critical role in promoting the pathogenic pathways leading to disease development. I hope I helped in building that understanding today. And just some additional points is that this makes primary dust characterization information critical to the definition of pneumoconiotic potency, and just the question of the relative influence of these parameters still remains open, and requires some active investigation.
Thank you so much, CK. Oh. Thanks so much, CK, for the brilliant presentation. I'll now open the floor for any comments or questions from the audience. I don't see anything in the chat so far. I see a hand. I must just. Okay, Prof. Ehrlich, you can go ahead.
Thanks very much. Can you hear me?
Yes.
Loud and clear.
Okay, yes. Thanks for a wonderful and elegant presentation. I have a question. So I always struggle to understand how much of coal workers' pneumoconiosis is silicosis, because of course there's a large body of literature on silicosis and silica. And you mentioned the American work showing that the resurgence of progressive massive fibrosis type silicosis is now being attributed to silica, a form of silicosis. But what you've shown today is that the restriction of the thinking and the research to, for example, pure silica in the laboratory would not be a correct approach. What you're trying to do is actually reproduce the interaction between silica, the organic component, and other minerals such as iron. So is the attention between these two approaches? One is to try and look at the effect of pure silica. Is there still advantage to that, understanding silicosis and therefore its other effects such as TB and perhaps even cancer, or going the route that you have, which is very interesting, which is to complexify it and see how much of the disease is being driven by the actual interactions between the different components of the dust in different ways. Thanks.
Thank you very much for your question and commentary. I think that the approach taken in terms of looking at silicosis and CWP would depend on what the pathological information would depend on how the pathological information is developing. And I say this because there is a tension in the literature between the time points at which some of the epidemiological data is being reported. So the study that I mentioned, which looked at incorporating the characterization information with the epidemiological data and trying to understand why there are different intensities of prevalence in certain regions within the US, was in the context of, I think, the first round of surveillance, epidemiological surveillance. So that was in the 1970s. And the mining modes, as well as the ore being mined in the current resurgence, is different. So they didn't have the context of the thin seam mining. And as they looked at the pathological reports, they saw that, excuse me, more of a prevalence of the, I believe, R-type OPSCs, which is characteristic of the silicosis type CWP. So while that is the American case, I think that there is still not enough data in different contexts to say that the intricacies and the complexity of the coal itself is not resulting in disease burden in other contexts. So I think that the literature can sometimes point to the fact that silica is the main agent and that should be carried forth, but there really isn't much other context that contrast the complexities of coal.
Thanks, CK. I see if Prof. Ehrlich needs to follow up, are you fine with that? Perhaps you can put in
yes,
the chat.
No, thank you very much. It's
okay.
Thought-provoking. Thank you.
Thanks, CK, and thanks, Prof. Prof. Rees and then Prof. Jibai.
Thank you very much. As Prof. Ehrlich said, very interesting. Really found it fascinating. It's nice to hear an expert talk about something they know so well. I have a very simple question, but it's of practical importance and I'm interested. Does your research say anything about the differences between bituminous and anthracite coals? I mean, in South Africa, for instance, I think there's a belief that the anthracite coal is more fibrogenic or causes more pneumoconiosis. Do you have a view on that?
So for the purposes of my study, I chose to stay within one rank. I chose to stay within looking at bituminous coal because I wanted to keep everything comparable. But I know that in literature, there is this idea that rank can influence the intensity of CWP progression, but that relationship was based off of correlative information, but it isn't necessary. My understanding is that it isn't necessarily, it doesn't have any sort of mechanistic weight.
Sorry if I'm taking too much time, but can you elaborate on that mechanistic weight? In other words, is it associated minerals that might influence the potency, or not the coal itself?
Yes. So what has been established is that between the different ranks, there can be a difference in the carbon-centered free radicals. So there was an idea that the carbonaceous matter could contribute to the overall burden of, or the impact of the radicals present in the system, because that is what is leading to oxidative stress. But the carbon-centered radicals in the carbonaceous matter are short-lived and then not necessarily reactive. So that is why studies looked at the mineral matter because they in the biological context react and lead to reactions that produce highly reactive radicals, such as the hydroxyl radical, or in the case of quartz, you have the silanol group, the silanol groups which produce highly reactive radicals.
Mm. Thanks, CK, for that. Prof. Jiba?
Thank you. I'm here with Prof. Adams in my office. Thank you very much for that wonderful presentation. So following up from the two previous questions, and you've identified that there aren't sufficient studies done within our kind of context to kind of explore these hypotheses further. So knowing what you know about where coal is deposited and the characteristics here in South Africa, what kind of additional information do you think that if one were to do these studies in our kind of context would come forth?
If I understand your question correctly, are you asking what kind of additional information would be needed to progress studies of this nature in our context?
No, I'm wondering, just postulating, based on what we know about the coal characteristics in our part of the world, what do you think, what kind of answers do you think they may show that thus far have not yet been sort of presented, or there isn't sufficient evidence for?
Well, in terms of our coal, we do have a lot of mineral matter. So I think that there is capacity to see a lot more mineral-related chemical effects showing more of the, how do I say, we might see more of the effects of that pathogenic pathway, the effects of oxidative stress and inflammation as a function of the mineral complexity in our coals that we wouldn't necessarily see in the American context, for example.
Thank you.
Thanks, Prof. Are there any other questions from the floor? Let's just check in the chat. Right, so we've got Vanessa Govender. CK says, thank you for the novel approach to the CMT diseases. Excellent thought-provoking discussion. And everybody else seems to be fascinated by your findings. I think from my side, CK, at the beginning, the introduction really had a very beautiful look at some of the American, European, and other studies, and a very good timeline of these. In our own context, even though there are few, what have you been finding, within a South African or African context? What's some of the work that has been happening over the similar timelines?
In the South African and African context, I really have not come across similar kinds of work. This is really work that I've mainly seen, again, in the American, European, Australian realms. And even in the European realm, the sample comes from China. So I really have not been seeing a lot of African-based studies.
Well, thanks for that. Prof. Ehrlich, you may go ahead.
Yeah, thanks very much. So there is the condition of mixed dust pneumoconiosis, which I think is sort of some controversy about how exactly to define it. It's used in different contexts, but the experience we had mainly from the foundries, early days, where there's a lot of iron. And one of the features of mixed dust pneumoconiosis was actually to disturb or change the normal clinical presentation of silicosis to a much more disorganized fibrosis, almost in some cases looking a bit like areas of bronchopneumonia. So that was a clinical epidemiological observation that iron in the process, for example, foundries, where there's obviously a lot of iron, would produce actually a different clinical phenotype. Whereas in the gold mines in South Africa, and this is part of my question, is iron not an issue because it doesn't seem to have produced this other clinical phenotype? In other words, is there a lot of iron or other confounding minerals in the bedrock of gold in our gold seams?
So Megan's actually brought this up, the issue relating to some of these iron-bearing minerals can be found in other types of deposits. And the conclusion that I've come to in my mind is that alteration and the context of the deposit must play a significant role in the material prior to inhalation. So either it is the form that the element is in, or the alteration state that it has endured prior to it being entrained as dust, or its association to different minerals, which may be inhibiting the effects within that particular ore.
Thank you.
Thanks, CK. I see Johanna and Megan are also in the audience if they would like to have any last comments or additions.
Hi. No, nothing from my side. I think it's, CK has done an extraordinary job with this work. It has been quite something to tackle, being truly interdisciplinary between science, engineering, and health. And it just shows what is possible, when you've got a really good student and now a early career researcher, Dr. Kamanzi. So yeah, it's been a really good journey, I think, for me, I think for all of us. But I have nothing to add. She's got this paper that she's submitting, I hope today. So the findings of her combination of the different approaches will be in that paper. So yeah, watch the space.
No, thanks. Yeah, thank you, Joanna. Please share that paper with us once it's out, CK. Megan, over to you.
So yes, good afternoon, everyone. I wasn't going to add to her what she said. I mean, any good piece of research creates more questions. So I think she's done some really nice work, exciting work. And yeah, as to what it is in different deposits, I think that's still an unanswered question. Thanks.
Thanks. All right, thank you so much, Megan. Thanks, Yuri. And CK, again, thank you very much for this fascinating talk. I think for our division, and in fact the school is at large, you've raised lots of questions for us to take home and to ponder on. So we'll probably be bothering you with many of our ideas as we think about those in the night as we ponder on your presentation. But thank you for the hard work and for having come through to join us. For everybody on the audience, thank you for joining this noon meeting. We'll see you again next Thursday at 12 o'clock. Thank you.
Thank you for the opportunity.
Thanks.